All right, cool. So as I promised last time, today we'll finally talk about SVM, support vector machines, which is one of the coolest algorithms in machine learning. It's by now a classic algorithm. It operates under the assumption, so it operates under the usual supervised, distributional supervised learning setting. So under the assumption that all the data is fully labeled for us. So all the data, assume that all the training data is fully labeled for us up front. Right, so it's motivated by margins and kernels, as we discussed last time. Okay, so I'll go through it in detail today. But we'll also start talking about more modern approaches to supervised learning, where the data is only where we only have partial supervision as opposed to full supervision. And I mean, as you see, I mean, this is super well motivated and very important topic in modern machine learning in the age of big data, where we have so much data that is basically hopeless to label it or annotate it all. Okay, and we'll start talking about semi-supervised and active learning. And actually, in particular, we're going to talk about, one of the algorithms we're going to talk about today is semi-supervised SVM. Okay, so everything fits well together. Great, so let's go back to the classics for now and talk about SVMs, right? So SVM is one of the most theoretically well-motivated and practically most effective algorithm in machine learning. It is directly motivated by the concept we've been talking about in the last couple of lectures, namely by margins and kernels. Okay, and in particular, just a very quick recap, because this will be crucial for the class today. The notion of margin I've been thinking about is geometric margin. Okay, and do you guys remember what is a geometric margin? What is a geometric margin? So if I have a separator given by normal vector W and the point x, what's the geometric margin of x with respect to that point? I'm sure you all know. It's just too simple of a question to answer. Yeah?
The closest
So,
simple x to the linear separator.
Yeah, so if you had okay, so you're answering a more complicated question. So you're answering if I have a linear separator, what is the margin of a linear separator with a set of points? What is the distance from the closest point to the separator to that separator? Yeah. Okay, so you're answering that question, okay? Yeah? The mic is not on? It should be on. You guys cannot hear me? It's strange. Maybe the batteries are running out. What's going on here? Okay, now I need some tech support. So let's see who is helping me. Tom, do you want to help me put new batteries? Okay, great. So, okay, speaking loudly. So what is a margin? So it's just a quick recap, you guys know. So right, just even going from an even simpler concept. So if I have a separator given by a normal vector W, the margin of an example x with respect to that separator is basically how far my example x is from that separator, right? And we argued in the class previously that we can always think about separators that go through the origin, because we can always translate the origin, right? So this is what I'm going to be thinking about today, separators that go through the origin. Okay, and so in that case, if I'm thinking about a separator that goes through the origin, and if my separator is specified by normal vector W, right, then the margin of an example x with respect to the separator is exactly the distance from the example x to the separator. And we've seen this last time. This is mathematically the same as, what's going on with the connection here? Our battery is running low. Okay, all sorts of technical problems today. Okay, but luckily I got. Okay, battery is also running low, but luckily I have everything with me. Just a second. Where is this going here? Okay. Great. Thank you. Hi. Okay, that's much better. Thanks, Tom. All right. Right, so we are thinking about separators that go through the origin, and we are thinking about geometric margins. So if we have an example, if we have a separator given by normal vector W, the margin of an example X with respect to the separator is simply the distance from that example X to the separator. And if we normalize the normal vector to have norm 1, which is we can always do evaluation of generality, then mathematically the margin is exactly the absolute value between that example, the absolute value of the dot product between that example and the normal vector. Okay, now this will become important when we put down the SVM algorithm, right? So this is a fact to remember, okay? And it's something that you learn in the 11th grade or something like that, okay? So geometric fact, good. So that's the margin of an example X with respect to a separator given by normal vector W. Is the absolute value of the dot product between W and X. Okay, now as your colleague said, and your name is? Peter. Yeah, as Peter said, right? So now, so I just defined the margin of an example X with respect to a separator, but now if I have a set S of examples, the margin of a set of S of examples with respect to a separator is simply the minimum, is the smallest margin of an example X with respect to that separator. Okay, and now I can also talk about just the margin of a set S, which is then just the maximum margin of a separator, of a linear separator with respect to that set S. So I search over all possible linear separators, and I take the one of maximum margin. The margin of a separator of my set S is exactly the margin of the set S. Okay? And we've seen last time that margin is an important concept in machine learning. It has interesting sample complexity and algorithmic implications. So we've seen that if the data truly has a large margin, or nearly a large margin, the number of mistakes that the perceptron algorithm makes depends entirely on the margin, and it's independent of the dimension of the ambient space. And it's also independent of how long the sequence of examples is, right? So if we have a large margin, it's a great world for perceptron, right? So if we have a large margin, then the perceptron algorithm behaves well. But we've also discussed that actually if we do have a large margin, so this perceptron algorithm is in the original form, it's an argument in the online learning scenario, right? But we've also discussed that people analyze the implications of margins in the more classic distributional learning scenario, or the data is all labeled for us up front, right? And we've discussed that intuitions behind the following type of statement. So we said that it was proven actually by Vabnik in the 70s, and very proven in various forms by various people, including Peter Bartlett and John Shaw Taylor. So it was proven that if my underlying distribution truly has a large margin, or nearly a large margin, then, and if I have an algorithm that is able, given a set of examples, that algorithm is able to produce a large margin classifier, which would one exist now, because I know that the underlying distribution has a large margin, so any sample is going to have a large margin, right? So if my algorithm is able to produce a large margin classifier, then I know that the number of labeled examples I need in order to achieve good generalization guarantees is small. It depends only on the margin. And again, this is independent of the dimension of the ambient space. Okay, so this is a very interesting sample complexity statement. It's kind of cool to know. And actually, it has immediate algorithmic implications. So this sample complexity statement, this type of guarantee actually directly motivated the support vector machines algorithm, the SVM algorithm. And basically, what this sample complexity statement implies, or this statement implies that somehow it's a good idea to search for separators that have a large margin, right? Because we know formally that they are less prone to overfitting. Of course, you can come up with some intuitive argument too, and people do this all the time, you know, somehow. But this is a totally formal sense in which it's a great idea, because formally we know they are less prone to overfitting. And also, it makes sense intuitively if you want to. I typically attach intuition to formal facts. Okay, cool. So this is exactly what we're going to do. So we're going to go through the derivation of the support vector machines algorithm. And what the algorithm just does, will search for a classifier of a large margin. Given a set of examples, we're going to search for a classifier of a large margin. Okay, and we're going to go like slowly through some of the actual derivations, because it's a super important algorithm. It's an algorithm that you definitely want to know. But all the details will now be simple, because we've spent a couple of lectures talking about margins, so hopefully you'll be able to follow. I think the details could be a bit scary at first if you've not seen margins and you've not been thinking what they mean, but after our preparation, I think we should be able to go through it. All right, so what we're going to do, right? Exactly, we're going to try to find a classifier that has a large margin. Okay, and for simplicity, just to start simple, let's think about the case when the data is truly linearly separable by a large margin. And let's assume that we also even know a lower bound on the margin, just to start simple. Right? Somebody tells me that gamma is a lower bound on my margin. Right? Then what we can do, we can write an optimization problem, right, like this one here. What I'm going to do, I'm going to search for a classifier specified by normal vector W. And I can assume with all of the generality that has unit length. So I'm going to impose it has unit length, my classifier W. And I'm just going to make sure that all the points are correctly classified. And they are correctly classified by the right margin. Right? And if you guys remember, I mentioned that the margin of an example when the length of the W is normalized to have unit 1 is exactly the absolute value of the product between that example and the normal vector. Right? So this is basically, I'm writing here the constraint that for all samples in my training set, right? So I have as input a training set of labeled examples here. Right? I have a fully labeled sample, training sample, and I have as input a lower bound of my margin gamma. And I can just write down an optimization problem, which is just search for a classifier specified by normal vector W. Let's assume that this classifier has unit length 1, and then let's just write down what the constraint that each single example in the training set is correctly classified and is correctly classified by the right margin, at least gamma. Okay, so is this clear? Just write down what we are searching for. I'm just writing an optimization problem. I'm trying to find a separator of margin at least gamma over my sample, because I know a lower bound on the margin gamma. And this is all fully realizable for now, right? Where the data, I assume that the data is truly separable by margin at least gamma. Okay? Now, of course, in general, I do not know gamma. So then we can just add this to our optimization problem, right? We can add it to our objective. We can just say, let's find now search over the maximum possible value of the margin gamma, again subject to the normal constraints that my separator has unit length and that it gets the normal vector has unit length, and moreover my separator gets all the points correct by margin at least gamma. Right? So all the positive points are on this side of this hyperplane, and all the negative examples are on this side of the hyperplane, and the margin here is at least gamma pictorially. Right? So is the formulation clear? I just draw mathematically down what we are looking for, right? And this is actually, in this form, it's exactly the optimization problem of finding a maximum margin separator of a given fixed set of examples in the realizable case where the data is truly linearly separable. Okay, so that's the optimization problem that exactly expresses what we want to express. Now, of course, we are going to try to think about how to solve it. And just a couple of comments. So this is actually a constraint optimization problem. Why? Because we have an objective here, or this is the objective function to maximize the margin gamma. That's the objective function. And these are my constraints. So I have a constraint that my normal vector is unit length, right? Which then helps me write down what is the margin, like under this unit length assumption, and I can write down that the constraint that each example has margin at least gamma. Right? So I have two types of constraints. One of them is that the vector has unit length, and the other one is that all the points are classified by margin at least gamma. Okay? Right, so it's a constraint optimization problem. You're probably familiar with such optimization problems. I'm sure you must have seen something like linear programming, right? Where what you are trying to optimize is a linear function subject to linear constraints, right? So if you had the linear programming type of optimization problem, then there are efficient polynomial algorithms to solve it. There are also efficient polynomial algorithms to solve something more complex, like convex optimization, where the objective function is convex and the constraints are linear. However, in this form, this optimization problem that I wrote here, so in this form, it's not a nice problem. Actually, the constraints are not really nice. In particular, can you guys see which constraint is not nice? I claim there's a constraint that is a bit nasty. It's not convex. The first one, right? So the first constraint here is not a convex constraint. Why? To have a convex constraint, I need that if a separator W satisfies the constraint, another separator W2, if W1 satisfies the constraint, and another separator W2 satisfies the constraint, then say any convex combination will satisfy the constraint, right? But what this constraint says, well, I need to be on the circle, so on this circle over here, right? And you can easily show an example like this one here, where you would have W1, which is an arbitrary unit length vector, and you can think about W2, which is the opposite vector. And if you think about their average, right, then it's a zero vector, obviously doesn't have unit length, right? So that's a simple pictorial proof of why this is not a convex constraint, right? So one of the constraints here is not very nice, so it's non-convex, and so we don't know general purpose techniques for solving non-convex optimization problems. Okay, so if we want to make progress and to get an algorithm that we can then run, we have to think about rewriting it. Okay, is this clear? Yeah? Okay, but here is actually a simple trick we can just simply, there is an easy way to rewrite this problem to make it convex. Okay, and here is the trick. So this is the original problem, right, where what I want to do, I want to find the separator of unit length, that maximizes the margin, right? Right, where the margin is specified by this constraint over here, right? Now, it turns out that if I define now a new vector W prime, a new normal vector W prime, which is simply W over gamma, then if I think about the length of W prime, because the length of W is 1, then the length of W prime is exactly squared, is exactly 1 over gamma squared. And so then maximizing the margin gamma is equivalent to minimizing the norm of W prime, right? And then, if I further divide, I want to also derive these constraints in terms of W prime, so I have to divide both sides by gamma. And so when I divide both sides by gamma, here's an equivalent optimization problem. Or what I want to do is to just find the vector W prime, right, such that such that these constraints are satisfied. The dot product between W prime xi times the label is at least 1, is greater than or equal to 1. And moreover, I want to minimize the norm of W prime squared. Okay, so let me say it again slowly. So this is the original optimization problem, or I want to maximize gamma subject to the constraint that the normal vector W has unit length and has the right margin, the right geometric margin, like in this picture over here, right? Now, this is a non-convex problem in its original form, but we can rewrite it easily to make it convex. And the trick is to just simply think about defining a vector W prime, a normal vector W prime, which is just W over gamma. Because W has norm 1, that means norm of W prime will be 1 over gamma, right? And so here we're trying to maximize gamma. This then will be equivalent to minimizing norm of W prime, right? Because norm of W prime is 1 over gamma, right? And then I'm just rewriting the second set of constraints in terms of W prime. And how do I do that? I just divide both sides of these inequalities by gamma, right? And then what I get is that what I need to do is to find the vector W prime subject to the constraint, these constraints over here, that this is called the functional margin of any given single example is at least 1. And then I minimize norm of W prime. Okay, so that's the new optimization problem. And pictorially, this is a picture associated to this optimization problem, right? So now I'm trying to find the normal vector W prime. I'm trying to minimize the norm of W prime, but then I also want to ensure that all the positive examples are on this side of this plane specified by W prime dot x equals 1. So I want all the positive examples to be above this plane, and I want all the negative examples to be below this plane specified by W prime dot x equals minus 1. Okay? So that's the new optimization problem, which is totally equivalent to the original one, which is what we wanted to solve. Okay, but now this is in terms of the functional margin, and now we're trying to minimize the normal W prime squared subject to the functional margin on any given single example is at least 1. Okay, and again, this picture is still for the realizable case, right? I'm still assuming that I can push all the positive examples on this side of this plane given by W prime dot x equals 1, and I can push all the negative examples on this side of this other hyperplane. Yes? Okay, but now the cool fact is that this new optimization problem actually, it's a convex optimization problem. And in particular, it turns out that it's a constrained convex optimization problem. So the objective function now is convex. It's in fact quadratic. And all the constraints are linear. And this is then a quadratic optimization problem that can be solved using standard techniques. Okay, do you guys actually see why this is why is the objective quadratic? Why is it convex? Why is it quadratic? Claim it's a quadratic objective function. So what is norm of W squared? Why did I even put a square there, actually? Why didn't I put just norm of W? I mean, because I could have just put minimize norm of W. It's the same, right? Doesn't matter.
Square makes it differentiable. I mean, you can infer the derivative of the quadratic form. But if you use L1, I mean, use absolute value actually is not differentiable at some points.
Yeah. Okay. This is true, right? Yeah, definitely. Good. So by the way, Travis is out here. He's an expert in optimization. So if you have a good. No, you're right. Okay, but okay. So let's. You're right. But let's put here. So okay, norm of W squared. Yeah, you're totally right. Well, why is norm of W squared? Going back to my original question, why is norm of W squared a convex function? So why is it actually a quadratic function? What do you mean by quadratic? So what are my variables here, right? The variables will be W1, W2, Wn, right? When W's are the coordinates, right? So I'm looking for a normal vector W. We'll have the underlying variables will be W1, W2, Wn, the entries of W, right? And why is this objective function quadratic? Because what is norm of W squared?
Actually finding the distance from the point. So while finding, you are taking the square root and finding the distance, it will be square function.
Sure, but okay, so again, why is norm of W squared a quadratic? Because what is norm of W squared? Is W dot itself, right? And if you expand that out, that will be sum of W1 squared plus W2 squared plus and so on, right? We only contain quadratic terms. Yeah? I was asking a very simple question. Okay, so that's a quadratic objective, and all the constraints are linear, and turns out that such an optimization problem is actually convex, and we can solve it. Okay, which is nice. Great. But this is still under the assumption that the data is linearly separable, perfectly linearly separable, still under the assumption that actually I can find a separator here that pushes all the positive examples on this side of the hyperplane, and a separator that pushes all the negative examples on this side of the hyperplane, right? But there are examples of data sets that are nearly separable, but this will never be possible, right? And in fact, this is actually an example, right? I have this positive example over here. And if you think about it, there is no separator that we're going to be able to separate them by a large margin, all the points by a large margin. Okay, so what do we do then, right? Of course, we can try to use kernels, but it could be an overkill, right? Because if I only have a few points that it's nearly linearly separable, I might be able to do something smarter here in the original space, right? And so basically, what is actually what we would want to do? I claim that really what we would want to do ideally, when you have the data is not perfectly linearly separable, you just have a few outliers. Ideally, what we want to do, we'd want to somehow find a separator of maximum margin that minimizes the number of mistakes. That's really what we want to do, right? But from the way I describe it, I already put in two objectives. I said I want to have a margin as large as possible, and I want to minimize the number of mistakes. So these are two objectives. So it's really a multi-objective problem, right? And I have to somehow trade them off, right, when I have a multi-objective problem. And the typical way to trade it off is to basically try to minimize the sum of these two objectives and according to weigh them somehow, right? Here I can also have a trade-off constant, right, that trades off between these two goals, two kind of potentially complementary goals. One is to maximize the margin, and the other one is to minimize the number of misclassifications. Either could be potentially contradictory goals, and so therefore I can just try to minimize, right, to add both of them into optimization problem as a sum according to, and also weight them by a trade-off constant. Okay, that's I claim probably what we actually would want to do in this case. It's a natural extension. Unfortunately, actually, it turns out, I mean, that sure, we can try to do so, but it turns out that once we have noise, finding linear separators that minimize the number of mistakes, even if I ignore a margin condition, it's just a very awfully computationally hard problem, right? So once I have especially adversarial noise, it's actually, technically speaking, it's amply hard to find a separator that minimizes the number of misclassifications. And this is true even if I ignore kind of a margin type of objective. And actually, this was a very cool result proven by, in a very strong form. Actually, it's very hard in a super strong form. And actually, Venkat Guruswamy, who is a theory professor here, and Prasad Gavendra, his former student. So actually, they proved in 2006 a very kind of really interesting result. It is a worst case result, but what they proved is, so say that you have a data set that is 99% linearly separable. So I promise you it's almost linearly separable, has some outliers. And the thing that I'm asking you, please find for me a separator that gets only 51% of the data right. So that's just a little bit better than random guessing by a constant gap. Well, it turns out that it's NP hard in the worst case. Okay, so this is what they proved in 2006. Okay, so once you have noise, especially adversarial noise, problems of handling noise, if you really care about the objective of minimizing the number of misclassifications, those problems could be super hard computationally. Okay, but of course, we have noise all the time in practice, and so machine learning people have smart ways to handle this. And in particular, one way to handle that has been used to handle it is to kind of replace this minimize number of misclassifications type of objective, which is a hard objective to deal with combinatorially, it's NP hard. We're going to replace it with a convex relaxation. Okay, and I'm going to go through this slowly. Okay, so that's the high-level viewpoint, but I'm going to go through it slowly. What do I mean by this? Okay, and I'm going to then present, now on this slide, I'm going to have the classic way to write down SVM once you have like a few outliers, right? Okay, cool. So we're thinking about the case, right, like in this example over here, where the data is actually not linearly separable, right? But we still are trying to find somehow a separator that has a large margin as possible, and somehow it's not totally gets SU points wrong as possible, right? And but as argued in this original form, this problem is actually it's an NP hard problem, but here is the classic solution, the SVM solution to this. Okay, so what we're going to do, right, actually if I go back, oh, what did I do here? Oh, I repeated the slide, I don't know why, but okay, good. So going back, good. So going back here, okay, let's just think for a second, go back and think about the realizable case, because we're going to just modify the perfectly separable case to handle noise in a specific way. Okay, so if you guys recall, I just talked about it. This is how the optimization problem will look in the realizable case when the data was truly separable by a margin, right? And so when what I was looking for a linear separator like this one here, specified by a normal vector W prime, and I was trying to minimize the norm of W prime and ensure that all the positive examples are above this hyperplane over here, specified by W prime dot x equals 1. And I was also trying to ensure that all the negative examples are below this hyperplane over here, specified by W prime dot x equals minus 1. Okay? So this is in the realizable case. Now I cannot, this is not going to be satisfied once I have noise, but here's what we can do. Well, ideally, we want to have all the positive examples on this side of the hyperplane. But if it's not possible at all, I'm going to allow them to violate this constraint, right, the W prime dot xi. So this is when y was 1, the constraint was that my example was on this side of this hyperplane, which means that the constraint was that W dot xi was greater than 1. Right? Now I'm going to allow some examples to violate this constraint by a certain amount psi I. This is called the slack variable. But I'm going to add this constraint to the objective function. I'm going to write for any such violation, I'm going to add to the objective function c times psi I. Okay, and these are called the slack variables. Yes?
Is that still W prime?
Say it again?
Is it still W prime?
Yeah, so actually, no, it doesn't matter here. Yeah, but, I use W prime because I was rewriting it, but it doesn't matter. I can use here anything I want. I can use U, I can use V. The name doesn't matter, right? As long as it's consistent throughout the same optimization problem. Yeah, but it's a good question, right? So it doesn't really matter. I should have actually here, I should have put W to be consistent. It doesn't matter. It's just a variable. As long as I consistently use it here, I can rename it here. Okay? Cool. So that's basically, again, so what I'm doing now, once I have a little bit of noise, I'm going to allow certain examples, certain positive examples to violate this constraint because I have no way around it. So I'm going to allow to violate these constraints. I'm not going to force that all the positive examples are on this side of the hyperplane. I'm going to allow them to be right here, like this example here, to be on this, to be somewhere in a different place. But right? So I'm going to allow them to violate this constraint, but I'm going to pay to the objective function. I'm going to add to the objective function with psi I, which is exactly by how much they violate the constraint. So pictorially, with psi I for this positive example is exactly the amount I have to move this point to put it on the right side of this hyperplane, as if it was a true positive example. Okay, that's the classic way to handle noise for SVMs. And so, right, and again, right, I'm going to also, as I discussed earlier, I'm also going to have, now I'm going to trade off these two objectives. One of them is, like, the first part here is trying to minimize norm of W squared, which is equivalent to maximizing the margin, as we discussed. And then the second constraint over here was ensuring that most of the examples have a large functional margin, right? So I'm going to, again, have a C, constant C that will trade off between these two potentially contradictory objectives. Okay, and just also want to mention that basically the modification that I did here, another way to think about what I did here, rather than penalizing, so in my original solution for handling noise, I was just trying to penalize an example. If it was on the wrong side, I was trying to get the example to pay 1. Now, but it was computationally hard to handle that. So now I'm not going to be able to do that. So instead, this would be like, this would be the, if I did so, if I penalize an example that was on the wrong side by exactly 1, this would correspond to kind of the 0-1 loss. Right? But it's computationally hard to handle. So instead, we're going to penalize this each example by using the so-called hinge loss. Right? This is what I'm doing here. So, which is basically, so this hinge loss exactly corresponds to the total distance I have to move the point to put it on the right side where it should be by the right margin. Right? So for example, for a positive example, if you go back and analyze here, for a positive example, so yi here would be a 1, right? For a positive example, I would, ideally I would have w.xi is greater than 1. If that's the case, then I pay nothing in this objective over here, right? If truly, right, if for a positive example, I would have w.xi is greater than 1, right? If I'm on the right side, by the right margin, I pay nothing, I pay 0. Right? If I'm right on the separator, right, if, for example, if my example is a positive example but has w.xi equals exactly 0, it's right on the separator, then I will need to set psi I to be 1. And so in that case, if it's, the positive example is right on the separator, we're going to pay 1, because then psi I will have to be 1 for this constraint to be a correct constraint. Right? So if it's right on the separator, I pay 1. If it's on the right side, by the right margin, the functional margin is at least 1, I pay 0. And otherwise, I pay linearly in between. Right? This is a so-called hinge loss. So basically, now I'm replacing the 0-1 loss with the so-called hinge loss, which is a convex upper bound of the 0-1 loss. And if I do so, then this problem that I obtain over here is a convex optimization problem. Because now I have, in the objective function, I have the sum of two functions, each of which is convex. So this is a quadratic function, and it will be a linear function. Okay? And again, this is very nice intuition, because this term that I had over here is exactly like pictorial looking over here, like what I pay for each example that is not on the right side by the right margin, what I pay is exactly the amount of that I have to move the point to put it on the right side by the right margin. And now the units here are like, this is the distance between, this is 1, so here is 1, right? So these are the units. Right, so basically, to make it a convex optimization problem, we're going to replace what we are trying to do at first, and it was NP hard, which is a minimized number of misclassifications subject to having a reasonably large margin. We replace that with this kind of hinge loss type of objective, where we just replace the number of misclassifications with the total distance we have to move the points to put them on the right side by the right margin. Okay, and then suddenly it becomes convex, and that's nice because now we can solve it. Okay, and this is a classic approach to handle support vector machines. Yes?
So when we add this new constraint to the algorithm,
Yeah.
would it affect the generalization bound as well?
Yeah, so that's an excellent question. So, okay, so this is how to solve all the data. We wrote the problem that we can write. So this is what we can solve over the training sample. But you are asking, what can I say in terms of generalization guarantees, right? That's actually an excellent question. Now, if there are two answers to this question, right? So, okay, so maybe when you do this replacement, maybe what we really cared about is minimizing the hinge loss. If we cared about minimizing the hinge loss, then I can apply classic machinery to the hinge loss function, and then everything will be great, right? So, right, okay, so we can apply generalization guarantees for the hinge loss itself, and everything is nice. However, if what truly I cared about is the number of misclassifications, it's not clear that there is an alignment between the number of misclassifications, right? It's not clear that if I optimize this, right, it's not clear that if I optimize the kind of this surrogate objective, I get something necessarily good about the original objective. Yeah, so, but actually you're going to have a homework question, but we're going to relate it to objectives. So it turns out that you can relate it to objectives. I'm going to put an extra credit homework question that is targeted for people like you. Yeah, but it's an excellent point. So this is basically like the traditional approach in the last, 15 years in machine learning is, well, let's notice that the original problem, maybe I have a problem that I truly want to solve. And I notice it's NP hard. Kind of what people did in the last 15 years, they said, oh, I'm going to write a convex relaxation, kind of a related goal that is convex, and that suddenly becomes easy, right? And then they kind of stop there. But you also have to think about, well, I write a convex relaxation, but how about the original objective? What am I guaranteed in terms of the original objective? Okay, and sometimes you can relate, like here you can relate, but not always, right? And so actually I think that there is a little bit of shift in machine learning these days. People are trying more straightforward to attack the original problems. So well, yeah, so we're going to try to find tricks to attack the original non-convex problem, maybe under nice assumptions. Okay, did I answer the question? Yes? Okay, in a long way, with a whole story. Good. But it's an excellent question, right? So I mean, algorithmically, people do, they're just going to rewrite, this is the original problem that maybe I truly wanted to solve. It's NP hard, I'm going to write a convex relaxation. Of course, I can solve it, but I also have to worry about how about generalization guarantees. And like there are two answers. You might just say, oh, when I relaxed it, maybe I truly only care about over the whole distribution, I only cared about having a small hinge loss. If that's the case, as small as possible, right? If that's the case, then I can just apply standard machinery. But if you really cared about the original objective, then you really have to relate the two. And it turns out that here, for this problem is possible, and will be an extra credit homework question. Okay, good. So, okay, great. Okay, and this is it's written in words that I just explained earlier. Okay, great. Okay, cool. So that finishes the discussion about, so this is basically SVM for the case when the data is linearly separable or nearly linearly separable. Okay, but we know that most data sets are not linearly separable. Okay, as we discussed, there are many ways to handle this, but here is, we also mentioned that kind of the SVM philosophy was to use a kernel. Okay, and do you guys remember what a kernel is? What is a kernel? It's a very cool concept. It's brilliant, actually. You should definitely know it. It's one of the coolest concepts. So what is a kernel? Yeah?
Phi of x comma z would be equal to phi of x into phi of z.
Perfect. Okay, so kernel function is just a pairwise similarity function that corresponds to a legal definition of a dot product, right? And we discussed why kernel is interesting because certain algorithms are kernelizable. They can be written so that they only interact with the data via dot products. And so if I have a kernelizable algorithm, that means I can replace a dot product computation with a kernel computation. I'm going to replace kind of x dot z of k of x comma z, which will I'll get the same behavior as if I map the data into the phi space and apply my original algorithm in the phi space, right? So it's an implicit, kernels are great, are special type of pairwise similarity functions that corresponds to legal definitions of dot products, and in combination with learning algorithms that operate only by dot product computations, they allow us to kind of implicitly access higher dimensional feature space. And why is it important to implicitly access the higher dimensional feature space? Because I get computational savings. I never have to go explicitly up. Okay, so that's a kernel function. Okay, and so we're going to try to use the kernel. And actually kernels, I mentioned this last time, so actually the idea of finding a separator over a large margin, it's very natural if you think about it. Even if you don't know about generalization guarantees, you might even come up with that idea, right? Moreover, even the generalization guarantees are known since the 70s. So people knew that you kind of generalize better, you are less prone to overfitting if you find a separator over a large margin. But somehow the idea didn't really take off because most data sets are not linearly separable. So really SVMs became popular once we had kernels. Because then we could use a kernel, and I could try to find a large margin to a implicit much higher dimensional feature space, and then many more problems are suddenly solvable from a practical point of view. Okay, so now can we kernelize SVM? Okay, so it turns out that actually in the original primal form, by the way, this is called the primal form, this is the natural form that we discussed. In the original primal form, the algorithm itself is not really kernelizable easily. It's not kernelizable. somehow because, I don't know, I have this normal W squared here, I don't know W is, so it's not obviously kernelizable. Okay, but there is a related form, it's a so-called dual form, Lagrangian dual form, but I'm not going to derive, I'm just going to tell you that it exists. And I'm going to point you to Andring's lecture notes if you're curious to see all the mathematical derivation. I'm also happy to describe it to you offline, right? But turns out that there is a, right, so this is the original primal form that we discussed. Turns out that there is an equivalent, the so-called Lagrangian dual form, that is kernelizable, right? So in this form, actually, so now I'm going to have, originally I had variables, so what are my variables? For W1, W2, Wn, or n was the dimension of the input space. Now in the dual formulation, I'm going to have variables alpha 1, alpha 2, alpha m, where m is the number of data points. And it turns out that the objective function looks like this. Okay, and the good news is that if I look at the objective function, I only need to, I have these dot products between training samples. I need to be able to compute xi.xj, right, to write down the objective. And so that's good news because it means it's kernelizable, right? So in order, what I will have to do is I'm going to replace this xi.xj with k of xi xj. Okay, so it turns out that in its original form, SVM is not, like in the most natural formulation, is not necessarily kernelizable, but you can rewrite the algorithm to make it kernelizable. Okay, and actually, if you go for the dual, Lagrangian dual, you're also going to observe, actually, and this is important to know, you're also going to observe that the W vector, right, the solution to this optimization problem can be written as sum of support vectors. And what are the support vectors? Are exactly the points, let me see, do I have right? The support vectors will be exactly these points that are right on the boundary, right on the margin, sorry. The support vectors will be exactly the points that are right on these hyperplanes. Right, so there are these two hyperplanes, important hyperplanes. I need to make sure that all the positive points are on this side, all the negative examples are on this side. Turns out, if you go through and analyze the dual, but actually can argue that the classifier that SVM outputs can be written as a weighted sum of these support vectors, so the points that fall right on these hyperplanes, this hyperplane and this hyperplane. Okay, and I guess this is interesting. Why? Because from a generalization point of view, there is another argument to SVM. It turns out it's a bit different from large margin. It turns out that if I have a small number of support vectors, I can again get good generalization guarantees. Because again, if I have a small number of support vectors, somehow implicitly kind of the search space is small because, right, I could only have a much smaller number of linear separators that are given by a small number of support vectors. Okay, so yeah, it's more like sparsity. The underlying solution is sparse. It's a different notion of simplicity. Yes?
But the margin is gamma, so how does it matter that there are many points on the boundary?
Yeah, you might have, they are kind of different. You might not necessarily have a large margin, but you might have a small number of support vectors. So it's a different notion of simplicity. I'm just saying that there is another SVM. People also like to talk about, I might have a large margin, large geometric margin. Or even if I don't have a large margin, even if my margin turns out not to be too large, but if the number of support vectors turns out to be small, kind of my final solution somehow is sparse, and it allows me to use different type of generalization guarantees. Right, so it's just a comment. People like to talk about that, like books, yeah. They are not quite equivalent. They are different notions of simplicity. Actually, having W sparse is equivalent to having kind of, when we wrote down the objective function in the primal form, here we really wanted W to have a small L2 norm. Like the W being sparsely corresponding to have a more L0 norm. There are different notions of simplicity and sparsity. Okay, so that's a very technical comment. Okay, I'm happy to tell you more offline. I just wanted to mention because people like to talk about, well, if I have a small number of support vectors and something nice will happen, there is an underlying machinery that explains all that. Okay, but the good news, and this is really what I wanted to get to, is that actually it turns out that we can rewrite SVM in a way that is kernelizable, just because I can have this dual formulation where I only have dot product computations that I need to compute, and I can just replace xi.xj with k of xi xj, and then suddenly, if I do so, I get the same behavior. So I basically get the same behavior as if I map the data into the phi space corresponding to my kernel and running the original SVM algorithm, non-kernelized algorithm in that space. Okay, and if the data is nicely separable in the space by nearly a large margin, I'm going to also get good generalization guarantees. Great, so any questions about this? Because, okay, basically this finishes the discussions about SVM, right? So, I mean, the derivation of the algorithm might seem a little bit technical, but actually it's intuitive, especially once you get the notion of margin. And it's a super important algorithm in modern machine learning. I think that for most applications, people would use SVM, actually, as one of the default algorithms. and with the right kernel. Like typically, you can use Gaussian kernel. You can try to do Gaussian kernel if you remember had a sigma parameter. You can try to tune it by cross-validation. You can try to learn a kernel. But in any case, it's definitely one of the arguments that if you have a machine learning problem, you definitely want to try to use it. So you must know it. Cool. So any questions at this point? And I'm going to post lecture notes. So Andrew has some great lecture notes. And I'm going to link them from the website. But yeah. They are much more, they go for all the derivation from the primal to the dual. And you have to go for Lagrangian duality. It's kind of really interesting. It's connected to game theory. If you're curious, come and talk to me about it. Okay, but I didn't want to go through the class for all those details. So questions or comments?
I have a quick question.
Yeah.
So when you had a large margin for like actually linearly
Yeah.
separable data, you would get good complexity guarantees. But if you have a large margin with slack variables, do you get the same thing?
Yeah, you get similar guarantees, right? So there are, I mean, it will depend, like again, like kind of the amount of slack, the kind of the guarantees will depend. Like probably need more if you have, like, yeah, it depends.
If everybody has slack variables, then.
Yes, it will depend on that slack. Yeah. So there is actually a great book. I mean, first of all, you can prove these guarantees by using Rademacher complexity, which is a notion that we discussed in class. So this is the modern way to prove it. But there is also a nice book. Actually, SVMs and kernels were like when I started my PhD was one of the hot topics, and so people wrote many books. There are at least 10 books on the topic. And actually, Alex Mola has a book, and also there is actually a great book by John Shaw Taylor and I think it's Nello Cristianini, and he has all the nice derivations of the generalization bounds from more first principles, which is before, not for Rademacher complexity. And there's all sorts of covering numbers and so on. So nice argument. Okay, so if there are no more questions, I'm going to go to the next topic, which is equally interesting. Okay, so, right, so, okay, good. So far, basically, throughout the course, we've been talking about learning mostly from fully supervised data. Right? So I mean, for like most of the algorithms that we talked about, like logistic regression or AdaBoost or SVM, right, operate under the assumptions that some humans sits down and labels for us all the data available for training. Okay, now obviously in modern machine learning that's really impossible because for most modern machine learning applications they have such massive amounts of data, of available data, that labeling or annotating it all is basically impossible. Right? It's just expensive and almost nearly impossible. So humans can annotate only a tiny fraction of all this, right? So for example, there are billions of web pages on the web. If you want to do some sort of text mining or web page classification, there are huge collections of images, right? And huge collections of data sets in computation biology, right? So everyone likes to talk about big data, right? So I mean, most machine learning applications have huge amounts of data, right? So it's impossible to label it all. Okay, now obviously one solution would be to just, take a small sample and label the small sample and only use only that sample for learning, right? That would be one solution. Okay, but it seems wasteful, right? Because ideally, what you'd like to do is to use somehow all the available data, even potentially unlabeled data, and minimize the need for human intervention, right? Use all the available resources in terms that you have for labeling, but somehow still try to use the other unlabeled data if there is structured need to do learning. Okay, and that's really exactly the motivation behind some of the more modern machine learning paradigms, like semi-supervised learning and interactive learning and never-ending learning and so on. And this will be kind of the topic for the next few lectures. Okay, so just very briefly before going into detail, so the semi-supervised learning scenario, which is again super popular when I started my PhD 10 years ago. So here we assume that in addition to labeled examples, the learning algorithm also gets to see a large amount of unlabeled data, right? So that's basically semi-supervised learning, okay? Or an even more a different type of paradigm that is also trying to use unlabeled data is the so-called active learning, where the algorithm will first get to see a large amount of unlabeled examples, but then it has the capability to interactively ask for labels of examples of its own choice from the pool. Right? And then again, the goal is to output a classifier of small error. Yeah, that's active learning. I'll come back to this, okay, in a bit. So these are like examples of paradigms that people have looked at. Yeah?
What is the difference between
It's an excellent question. So the difference between active learning and online learning, right? So in online learning, first of all, so typically in active learning, people think about distributional guarantees. So here in active learning, we're still going to assume that there is an underlying source of data, and I get examples from that source, and I want to do well with respect to examples that come from that source. Okay, that's one. While in online learning, typically you think about worst case inputs, number one. Number two, in active learning, I also first get to see a large amount of unlabeled data. Right? In online learning, what you assume that you get to see is it's just each day an example comes in, like an email message, I have to make a prediction. Right? And then the next day, I learn something, the next day another example comes in, I need to make a prediction of that one, and so on. Right? So I only get the examples sequentially. Like in active learning, what I get to see first is the unlabeled parts of my examples. So that's a lot of information potentially. And then what comes in the sequential manner, in adaptive manner, is the label. Okay, so they're a bit different. But there are connections. And of course, you can also think about online selective sampling. Like you can think about online active learning if you want to. Okay? Yeah?
So just as an example, like incoming flow stock ticker prices, that could be an online data source, right? Because you can make a prediction about
Yeah. Yeah.
based on the
Sure, sure,
and the prices you've seen
sure.
in the past hour. Right? That would work.
Yeah, definitely. Okay, cool. But so today, so I'll talk about active learning in the next lecture. Today I want to go and talk about semi-supervised learning, which is an even more basic paradigm. But I mention them because they both have in common the fact that they use unlabeled data. But actually they use unlabeled data in different ways, potentially. Okay, you can also combine the two if you wanted to. Okay, good. And there are other paradigms that use partial supervision, like multitask learning, lifelong learning. Okay, so other subtle ways in which partial supervision or unlabeled data is helpful. Okay, cool. But let's go slowly through semi-supervised learning. Okay, so first of all, do you guys believe me that many of the modern machine learning applications have huge amounts of data? I mean, I think it's almost obvious. I even have, yeah, like, yeah. There are so many, yeah. It's obvious. Most machine learning data sets have huge amounts of data. Okay, you can read some of the examples here: computer vision, computational biology, and so on. Right? Data is generated all the time. I'm sure you all read the news. Okay, great. Well, because of that, actually, semi-supervised learning has become a prominent paradigm in the recent years in machine learning. Okay, and I'm gonna have it actually. Yeah. Okay. Good. So just to be a bit concrete, because we also want to understand, of course, we want to see algorithms that use semi-supervised learning, but we also want to understand what is the underlying kind of modeling assumption. So more specifically, so here is my picture, right, of what semi-supervised learning is, right? So the typical channel for supervised learning is we have some source, underlying source of examples. In the training phase, first, a random sample of those examples are labeled by an expert. Right? This is the usual supervised learning. So I get basically a data set of labeled examples. These examples are drawn ID from the underlying source, and they are labeled by an expert according to some fixed but unknown target function. Right? That's the typical channel for supervised learning, and this is what we talked about throughout the course mostly. Okay, except for one lecture where Tom had some semi-supervised learning, but except for that lecture, we mostly talked about supervised learning. Okay, this is the typical channel. Now, in addition to this typical channel, we also assume in semi-supervised learning that the algorithm can also access a large amount of unlabeled data. So it can also access a large IID sample of examples drawn at random from the underlying source. Right? So in addition to labeled samples, the algorithm can also access unlabeled samples coming from the same source. Okay, and the goal is the same as before, to find the classifier that has small error rate. Right? So I mean, you want to find the classifier that has a small error rate with respect to points that come from the same underlying source. Yeah, but the question is, can you use unlabeled data? Can you leverage unlabeled data somehow in order to achieve your goal and do better than if you only looked at the labels? Okay, so that's semi-supervised learning. Okay, and it's kind of a really interesting paradigm, and yeah, and I guess I would claim that it's at first, I mean, at the beginning, it might be a bit unclear what unlabeled data can do for us in semi-supervised learning, right? Well, in active learning, like when you are active, the other paradigm that I mentioned, we're going to talk about more in detail in the lecture. In active learning, somehow you can, you have the ability to focus, right? Because you can get specific, you can get a choice to ask for labels of examples of your own choice, and maybe you can focus somehow on what you realize at some point that are harder parts of the instance space, right? So there you can kind of imagine why unlabeled data could be helpful, right? Because I get a feel of where my data lies, so maybe I have some confidence based on what I've learned so far, and I'm asking for parts of the instance space or the data I'm more or less confident about. So there it's, I think, more obvious why unlabeled data can be helpful, okay? But how about the semi-supervised learning setting? So what can unlabeled data do for us? Right? Because here all I have is I have a random sample of labeled, a small random sample of labeled examples, and I have huge amounts of unlabeled data. How can that help us for learning?
Because we can retrieve the population distribution of the unlabeled data, the response. Right?
Yeah, so it can tell us something about the marginal. Okay, good. But perfect. So it can tell us something about the marginal distribution. But why is it that if I know something about the marginal distribution, why do I get any information about the label function? Right, so that's an excellent point. It gives me information about the marginal, about the underlying distribution of our unlabeled samples. Right? That's excellent progress. Yeah, that's definitely a good point. But then why is it helping me to predict the label? Why knowing something about the marginal helps you to predict the label?
Because the sample is retrieved from IID. So if we predict something, actually we are sampling from the distribution. So we
Yeah, so you learned.
the probability of how they belong to this distribution. But I'm not sure. Yeah. I don't know exactly.
Yeah, but anyway, so it's an excellent point, right? So what your name is?
Kelly.
Kelly, right? So Kelly makes an excellent point. What unlabeled data can help us is understand is the marginal distribution, right? The distribution over the unlabeled samples. Yes?
Is the distribution of positive and negative labels on the labeled data is the same as the distribution of the unlabeled data, then we can say that our progress is going in the right direction.
Okay, but in what sense?
I believe like it's just doing the clustering, to put in simple words. Like it is clustering the data in different parts, and then we can use supervised learning or.
Okay, cool. So you have right intuitions. All of you have right intuitions. Little bit of so good pieces about unlabeled data is helpful. It turns out that actually unlabeled data is helpful more generically. Right. So clustering type of cluster assumption is one assumption of unlabeled data is helpful. Okay, but there are other types of ways in which unlabeled data is helpful. Okay, so it's not the only way. Okay, so basically at a high level, basically, as a key insight, unlabeled data is helpful somehow if we have beliefs not only about the form of the target function, like it's a linear separator, but if we have additional prior knowledge or beliefs, we know more about how the unlabeled data relates to the underlying, to the target function, right? And this will become very concrete in a minute, okay? Because there are many ways. So basically, unlabeled data is helpful if we have beliefs not only about the form of the target functions, or if we have prior knowledge not only about the form of the target function, but we also have prior knowledge about how the target function relates to the underlying distribution. Because if there is no relationship, in the worst case, it might not help at all. Okay, and just to mention, just to advertise it, actually, so this was a super hot topic when I started my PhD, and Tom actually was one of the, I think, the leaders, maybe you're even the one that promoted it. Right, so, and many people are thinking about, yeah, you're the leader, I think, that's the right word. Good, right, so, good. So, right, so it turns out that it was so interesting that many people, most all of the machine learning community was thinking about ways to use unlabeled data in the learning process, right? That's clearly the modern way to go. And many people develop many algorithms, and I'm just gonna write down on the slides three types of algorithms that use very different types of assumptions about how the unlabeled data relates to the target function. Because they all implicitly use different types of regularity assumptions or beliefs. Okay, and so the first one is what I'm going to go through today. It's called the transactive SVM or semi-supervised SVM. There's another one, the co-training algorithm, due to actually Tom Mitchell and Avrin Bloom. And there's another family of methods called graph-based methods that was actually originally due to Avrin Bloom and Shuchi Jwala, and then it was popularized by many others. So, there's a lot of activity, like in machine learning in recent years on the topic. And so it was really kind of the hot topic in machine learning. And in fact, I need to point this out, actually, all these papers that introduce this. So I mentioned there are 3 big families of algorithms, and each of these papers got a test of time award at ICML. So I find this really cool. It shows how important the topic was. So do you guys know what the ICML is? It's the main conference in machine learning. And like I think in 2008, they introduced something called test of time award, where they look back 10 years and they were thinking about what is the most influential paper from that ICML 10 years ago. And they picked one. And in the very first ICML, the one picked was a semi-supervised learning technique by Avrim and Tom. It was actually a Cold paper, a learning theory paper. But they decided that the best machine learning paper in that year was at Cold. Okay. And that was in the first time when they had the test of time award. And the next year they looked again and what was the best paper in ICML, the one that had the most impact from ICML 99 turned out to be another semi-supervised learning paper. Okay, and so on. So like basically it's kind of really cool that like out of, they only had like, I don't know, 7 test of time awards, half of them were on semi-supervised learning. Okay, so you guys can see how important the topic is. Okay, so that was my advertisement, but it is really a cool topic. It's important to have good algorithms and understanding of what unlabeled data can do for us. It's also conceptually really interesting. Yeah, and by the way, Avrim Bloom here was my PhD advisor. So super cool, very insightful learning theorist. Okay, great. So now, okay, let's go and try to go through basically one of these algorithms, a semi-supervised learning algorithm. I'm going to start with the one that I think it's potentially, given the discussion today, is the most intuitive one, and namely the semi-supervised SVM, right? So as I mentioned, unlabeled data can help us if we have beliefs not only about the form of the target function, like it's a linear separator, but if we also have beliefs about how the target function relates to the underlying distribution. Okay, and the natural assumption, which is a bit related to what you're saying, is just to assume some sort of a large margin assumption or some sort of cluster assumption, which is to believe that the target function doesn't cut through high density regions of the space. This is actually implicitly the assumption that underlies the SVM algorithm, right? And just to stay simple, let's assume that we believe that the target function is in fact a linear separator, right? Just to stay simple, we can always kernelize and do everything fancy that we want, right? Okay, so here's the picture, right? But actually I think this picture should really clarify one unlabeled data can help us. Okay, so here the belief is that not only the target function separates the data, right, not only the target function is a linear separator that separates positive examples from negative examples, but it does so by a large margin. Okay, when I claim, and this is very much the way you're thinking about it, your name is? Hirsch. The way Hirsch is thinking about it, right? And when I claim that basically unlabeled data is here helpful because conceptually speaking, it can help us throw out hypotheses that cut through high density regions of the space, because we know they cannot be the target function. Okay, and let me go more slowly through this example, right? So let's assume that we truly believe that the target function separates the data by a large margin. Okay, then if I only have a small number of labeled examples, like 4 labeled examples over here, this separator over here would be the one of the largest margin and could be a very plausible function that my algorithm might output, my SVM algorithm might output, right? But then if I start seeing unlabeled points, like in the second picture over here, then I can immediately notice that basically this is not a reasonable classifier after all. So I should just discard it, right? Because it doesn't have large margin with respect to the unlabeled data, right? So I can easily discard that from consideration. Okay, so now once I have lots of unlabeled samples, and I realize that this separator over here is actually not a good separator, and because it cuts through high density regions of the space, and instead, right, then I can just, if I have a few labeled samples and lots of unlabeled samples, then in this example I would converge to the, if I find the separator that maximizes the margin over all the data and gets the labeled data right, in this case I would get the right separator. Yeah, so is this clear? So this is, I think, a very cool picture that explains why unlabeled data is helpful if we have the large margin assumption. Because basically it can help me discard, so from a small number of labeled examples, this classifier will look very reasonable, because it has the largest margin over that small data set. However, if I see lots of unlabeled points, right, so these dots for me that don't have labels on them are the unlabeled points. If I see lots of unlabeled points, I realize this is not reasonable, and so I can discard it from consideration. Okay, that's a picture. And this is exactly what the transductive SVM algorithm does, or the semi-supervised SVM algorithm does. It's exactly trying to find, so if now I have as input a set of labeled examples, right, and I have potentially a much larger set of unlabeled examples. And what I'm trying to do is to find a separator that has a large margin with respect to both labeled and unlabeled data, and gets the labeled data right. Okay, now I'm going to write, I'm just going to, given everything that we've talked about so far, we can just even write down the optimization, the corresponding optimization problem. Okay, let me just write it for the first for the case when it's true, the data is truly linearly separable, and then we can always add the slag variables, right? The more fancy stuff. Okay, so basically, if we only had labeled data, then we discussed that what we'll try to find is a separator. Well, this is the final form that we had. We're gonna try to find the normal weight vector W. We're trying to minimize the normal weight W, and we're gonna try to make sure that all the points have functional margin at least 1. Right? This is all if we have only labeled data. But now we also have unlabeled points, and right, for the unlabeled points, what we want them to be far from the separator, but we don't care on which side they are, right? So basically, all I want to make sure with the unlabeled points is either on this side of the separator, or so above the separator of W prime dot x equals 1, or below the separator of W prime of W dot x equals -1, right? And basically, so this is what I care about. And one way to write this is to then put fake labels on the unlabeled points, and then just to ensure that this is satisfied, which mathematically just means I just ensure that basically my unlabeled points are far from the separators. Okay, so that's one way to write down. I'm writing down the optimization problem. The convex optimization problem is it's not convex actually. I'm writing down the optimization problem. It's not convex anymore because of this. I have new variables here. The constraints are not linear anymore. Okay, but in any case, so you can write down, and this is what Thorsten Joachim in his 1999 paper, the celebrity paper did. He wrote down an optimization program that exactly corresponds to the intuition that what I want to do, if I believe that my large margin assumption is satisfied and I have lots of unlabeled data, then what I want to do is to try to find the separator that has maximum margin, both over labeled and unlabeled points, and that gets the labeled data right. Right? And right. All right, and this is, okay, so this is the optimization problem written for the case when truly the data is linearly separable. Now, if the data is not linearly separable, then I just need to do the same tricks that I did earlier, just introduce the slag variables, right, in the same way. And I'm going to have slag variables both for labeled and unlabeled points, and then I'm just going to try to solve this optimization problem. Okay, so that's, yeah?
In this case, we are taking the same weight on both labeled and unlabeled.
Oh yeah, you can put different, okay, perfect. Actually, so you are making a good point, right? This is the constraint that I'm adding, but I also need to add slag variables, right? And I need to, right, you could potentially put different C parameters over here.
We should have more weight on the labeled.
Yes, excellent point, yeah. So, and people have tried that. Excellent, yeah. I always like your question. They show that you follow, guys. Right, so you're right. Actually, I could have had here C1 and C2, and I bet that in his original paper, Thorsten had that. Great. Okay, but it turns out, so that's good, that really captures, right, and what we really want to capture, but it turns out actually that because of these unlabeled points, and now because intuitively now have to put fake labels on these unlabeled points and kind of try to put possible fake labels and kind of try to find the best possible labels, because they're trying to find the best separator that gets the unlabeled data right by the right margin, somehow we have a combinatorial explosion. It turns out the underlying problem is NP hard. It's again hard to solve. So while for SVM, when we have the pure supervised SVM, when we wrote with slag variables, right, it was a convex optimization problem, so it was solvable efficiently in polynomial time. Now, once we have unlabeled data, because we have these choices kind of on which side, right, I have this choice, should I put an example on this unlabeled example here or here, right? Because of these choices and because we have many unlabeled points, then suddenly becomes NP hard. Okay? In this form. But that didn't stop, I guess, Thorsten in his original paper showed the underlying optimization problem is NP hard, but he did come up with heuristics. So it's a mixed optimization problem. It has both integer constraints or like integral constraints and also real constraints, and you can try to use like some sort of branch and bounds, or all sorts of heuristics that people have in optimization community in order to solve the problem. And he did so, and he did show it on text classification data sets. If you use this algorithm with lots of unlabeled data, you do better than naive Bayes and logistic regression and all the competitors. Okay, and so yeah, so the original natural formulation is not solvable in polynomial time, but of course you can try to solve it by using heuristics. And if the data is nice, then that's good. And actually, I think I'll have to check, but I think that since then people actually have come up with approximation algorithms for this. So there may be ways to get approximation algorithms. I think there was a Call13 paper that did that. I'll check that and tell you next time. Okay, cool. But actually, I want to also mention actually an important point here. So So this is the optimization problem that people had, right? But you might also, okay, so of course I can use my unlabeled data algorithmically, but I also want to think about when is actually unlabeled data helping me. Is unlabeled data always helping me? Sure, under the large margin assumption. For now, let's stick with the large margin assumption, right? Because there are many other beliefs that you can think about, and we'll talk about them next time, including we'll talk about Tom's algorithm, the code training algorithm. But let's stick with the large margin assumption that you can still ask the question, when is actually unlabeled data helping me, right? Is it always helping me? Is it true that it's always helping me? So let's assume that truly the target function has a large margin. Is it always helping me, or is it only helping me if the distribution is kind of nice with respect to my belief and my target function? What do you guys think? When I started my PhD, I went to an ICML workshop on semi-supervised learning, and people were making all sorts of claims. Unlabeled data, oh, here is on my data set, unlabeled data helps me. On this one, unlabeled data helps me. And I had all these fuzzy claims, and they were all excited to use unlabeled data, but they had fuzzy claims, and not necessarily a way to formally talk about it. So I got really interested in formalizing semi-supervised learning. And it turns out that actually you can formalize and talk about it formally. But one of the key questions that I was thinking about is, actually, it's unlabeled data always helping you, even if the underlying, even if the belief that, for example, in this case, the belief that the target function is a large margin satisfied, is it true that it always helps me, or it only helps me if the data is nice?
If you're sure that there would be a large margin, then it will always help you. If you're sure about the margin.
Yeah, so that's a good question. Even so, it might not always help you. It's significantly, okay? And here are a few pictures. So first of all, but you are going, you're perfect actually. So so let's assume I'm trying to use semi-supervised SVM, right? That kind of operates under the assumption that data has a large margin, right? If the assumption is not true, like it's random noise, like uniform, like the underlying distribution is uniform over here, even the target function is a linear separator, then I know I'll need lots of labeled samples, even if I don't use that. I need the number of labeled samples will depend on the dimensions of the original input space, right? So I need lots of labeled samples even, in the purely supervised setting, and unlabeled data are not going to help me at all here, right? So if the assumption, the large margin assumption is wrong right at the start, then obviously I'm not going to get any benefits. But let's assume that the large margin assumption is correct. Then I still claim that unlabeled data doesn't always help you. Right? And here is an example, because you can still have 1 over gamma squared cluster separated by margin gamma, right? And you still need to see, so the label complexity would be 1 over gamma squared, we know that, but you still need to see a label point in each of the clusters. Okay, so that's an example where even if the large margin, it could be my target function is any of this, but there's a large margin, at least gamma, but because the data is clusters, so that I have 1 over gamma squared each of, 1 over gamma squared clusters, and the label there, the target label there can be anything, I still need to see a label point there. So even if the assumption is satisfied, unlabeled data might not always help me. But if the distribution is nice with respect to my assumption, like in this example here, if the distribution clusters nicely and I only have much fewer clusters that are separated by a large margin, then suddenly I get lots of gains. Because informally speaking, all I need to see is a labeled example per cluster. And so if I have if the underlying distribution is given by a small number of clusters separated by a large margin, then I can use lots of unlabeled data, polynomial number of unlabeled samples, and one labeled example per cluster, and then I could learn well. Okay? With small number of labeled samples, and really leverage unlabeled data. Okay, so what this slide is showing that actually unlabeled data is helping you if you have additional beliefs about how the target function relates to the underlying distribution, number one, but also the underlying distribution has to be nice with respect, somehow it has to have some additional niceness properties for unlabeled data to help you over labeled data. Okay, cool, and so that's, right. And yeah, so we'll start from here next time. So basically, Joachim Storsten showed experiments of this method, and then there are some really cool other techniques like code training, and also some techniques based on graph-based semi-supervised learning, where you can use unlabeled data to somehow glue similar examples. And yeah, we'll talk about this next time. So turns out that it's a really, really interesting topic, and lots of cool algorithms have been developed. Okay, great.